Welcome to the last lecture. Since I'm often over time at the end, I will start with some final comments now so that I don't have to give them when everyone is tired. First of all, I have done far less in this lecture so far than what was indicated on the table of contents. I will provide a new table of contents where I just list keywords on everything that we have been, that I have presented. This might take a while, but I will send it to you as soon as it's finished. Then, somewhat related to that, any comments that you have on anything that I was talking about are most welcome. It will be convenient if you give the number of to which it refers. Specifically, let me know if you want to have more references for some concrete issues, and maybe also whether you are interested in a continuation. At this point, I don't have any concrete plans, not even any plans for continuation, but it's not excluded. At some point, I will have to make a decision, and for that, it would be nice to have some feedback.
You will come back to China?
So no. I will leave next Monday, and at the moment I don't have any plans, in particular no concrete plans. But if I understand correctly, I would be welcome to come again. You know, all of this is via short emails. There's no.
Well, next time.
Let's start.
Yeah.
Today we have a separate chapter or section 5, which I call a stringnet modular functors. And this is a combination of aspects where it's mainly about modular functors and stringnets, but then also application of conformal field theory, in particular to correlators, in a complementary way as to what I have done on Tuesday. So let me first lay something general about modular functors. There are different possible definitions, and I will mention, comment on that a bit later. But for now, I just give the definition to start with, and I will modify this in a few minutes. So the first version is a modular functor, which, by the way, is not an ideal word. But it's what people use. It's functor from the cobordism category, where objects are one-dimensional manifolds to vector spaces over some field, often the complex numbers. So to a one-manifold, compact, smooth, oriented one-manifold, we associate a vector space, and to a cobordism, in the sense I defined a long time ago, we associate a linear map between the vector spaces associated to the incoming and outgoing part of the boundary. And we also require that this is symmetric monoidal. Remember that on both of these categories here, we have a symmetric monoidal structure. Now, for me, this is in two respects not yet good enough. The first is here we need about closed manifolds. Non-manifolds, I would like to admit also what I will just call here physical boundary in the same sense as I used on Tuesday, and this corresponds for the category here to allowing not just for disjoint unions of circles, but disjoint unions of circles and intervals. And analogously then for the cobordisms. This to some extent means that we allow, in particular for cobordisms, which not only can have boundaries but also corners. And because of that, we want to maybe I write this. We extend this to the 2-1-0 situation. And concretely, this means that we instead deal with bicategories, not categories, and corresponding functors. Functors between bicategories are often called pseudo-functors. But I will use the term several times today, but not always write it, because it's really the right concept of functor between bicategory. And I will introduce this. So we first need the notion of a bicategory. Category is noting that we have 2 levels of structures, objects, and morphisms. In a bicategory, we have 3 levels. Maybe I mention here also possible references, Leinster and Chomapries. Of course, you find it also in many other places. So you have the following data here. At the first level, there is class, which we call again objects. We call the bicategory by a strip B. And then at the next level, we have at the next 2 levels together, we have for any pair AB of objects, we have a category. Sometimes for the home category and abbreviated hom AB, if we want to indicate that the name of the bicategory as we provide here. So this is a category, so it's itself a 2-layered structures. So we have here objects of the home category, and these we call then 1 morphisms of the bicategory, and we have morphisms which we call 2 morphisms, or also 1 cells and 2 cells, but I will use 1 morphism, 2 morphism. Then together with the category, there comes a composition of morphisms, so a composition of 2 morphisms, and that we call the vertical composition. Maybe I should write your composition. And I will note it by a circle. for the space, as you can imagine, for the horizontal composition, and the notation for those is not uniformly different. So I will use this symbol, and then for any triple ABC of objects, there is a composition functor. Which I denote by C, ABC, which composes from AB and from BC to from AC. So both for objects and for morphisms. And now I need notation for that. And the notation here is that, well, the objects I call GF, because there are now one morphisms, and this is mapped to G composed with F. And I use the same circle as here, but then I need for two morphisms, I will use a different symbol, namely star. The reason for this extra new symbol is that, well, it's a new composition of two morphisms. So I need a different symbol, and this is called horizontal. And you may complain that I use the circle symbol here for the one morphisms, and here for the other composition for the two morphisms. But you will have to live with that. And then, in addition, one more aspect for every object. There is an identity functor. Which I denote by I with index A, which starts from the category 1, by which I mean the category with a single object, which for which I use the symbol, and a single morphism, which then has to be an identity to the endo-hom category for A. Since this is a functor, this means identity sent to identity, so this sends. This is the reason why we call this identity. And then, still not finished, there are natural isomorphisms. Which, if I would use them, I would call A, UL, and UR, which are analogous to the associator and uniter for monoidal category. So, for example, we have A, H, G, F as a component, which is now at a two morphism from this composition of one morphism to a possible composition, assuming that they are composable, and analogously for U and UL and UR. And then we have axioms, which are just a pentagon and triangle for this structure here, which are analogous to what you have in the monoidal category. And if you have the impression from this that this is very similar to what you have in monoidal categories, here I have guessed right. Namely, monoidal categories can be seen as particular example of 0% of bi-categories. One way to see this is by using a graphical calculus, and then we do it that way. And the graphical calculus, like for monoidal categories, is for strict bi-categories. Strict meaning that these natural isomorphisms are in fact identities, and just like for monoidal category, there is a strictification result, and that you find, for example, in a paper by Gordon Power Street. And this is a long paper, so reference more precisely. Strict bi-category is also called a true category. And how do we do a graphical calculus here? We take the same type of canvas as for monoidal category, so it's some rectangle, and then we say we have one morphism, which we indicate by line, so it could be an F, and so previously these were this would correspond to objects. Now they are monomorphisms. What about the objects? Well, these are, if F goes from A to B, then we label the two cells of this stratified manifold by the objects, and we read them from right to left. And analogously, if you have a true morphism, say alpha from F to G, or better from H after G to F. So I have written down. So we have H and G here. So composition is here from right to left, and then we have F here, and then we will have alpha and there. And in this case, say if G goes from A to B and H goes from B to C, then F will go from A to C. And if you want to know more about the graphical calculus, you can look in again at many places, but I mentioned in the list, which will be completed today, by Hinz and Marston, and also if you look at a paper by myself, Christoph Weigert, and Yang, the second of the two that are in the list, then that's section 2.4. And now, if you look at the situation that we have only a single object, use again this symbol here, then we need it here, and in any two cell of the stratification that we have. And since it's the same level everywhere, we can just ignore it, and therefore we get pictures as we have monoid. And indeed, now we can formalize this by associating to monoidal category a bi-category B, which is called BC, and this is called the D-looping of C, where just the objects consist only of a single one, and then there's only one home category, which is C. And just like we now have an additional level of structure for categories, bi-categories, there will be an additional level for functors. So if you say we have a functor, and as I said, often this is called a pseudo-functor, f from B to B prime. And then this consists of the following things. First of all, an assignment of objects to objects. For every object A and B, of course, then there is a functor f A B from the home category with respect to B of A and between A and B to the corresponding home category in B prime. And there are invertible homomorphisms which we call phi A between the identity of f of A and f of the identity of A for any given A. So if we would deal with ordinary functors between categories, part of the definition would be that it's the same. Now it's the same up to. So now we are talking about one morphism, and they have to be the same up to an invertible two morphism, and analogously for composition of morphisms, and will be an isomorphism, invertible two morphism from f of g after f of h to f of g after h. And maybe I should write here prime because this is prime. Now back to why we are doing that. We had this definition of monoidal category of modular functor, and so now we have bicategories. So we need, if we want to generalize modular functors to that setting, we have to get analogs of the categories we have there, which are now bicategories. And so we first need a bicategory, which I denote N as as before, but now with a script C here, and I added B here for indicating that I have a boundary plus one manifolds. And this is the following data objects are compact oriented smooth one manifolds. So this means finite disjoint union of circles and intervals, which I denote by S1 and I. And to be precise, we think of this as the unit circle in the complex plane, and this as the unit interval, say from 0 to 1 on the real numbers. And then we have in circle, when we want to describe a cobordism, then we deal with embeddings of this concrete one manifolds into the two manifold, of which the cobordism, which underlies the cobordism. And one morphisms are compact oriented smooth surfaces, possibly with boundary. We'll call an object of an L. So here we have now morphisms L to L prime, and those I will typically denote by sigma. So these are compact-oriented smooth surfaces with possibly with boundary, and a parametrization of not a boundary but a certain subset. If to say more about this, of the sigma. And parametrization simply means that I have embeddings of objects into this one manifold. But I do not need to fill out all of this sigma. There can be some rest, and this rest corresponds to the free of the single boundaries. So in short, a cobordism of a slightly more intricate type than what we had before. And then two morphisms. Isotropy classes of diffeomorphisms. And often I will denote them by, well, not so often actually, but someplace maybe by small gamma. So this is a diffeomorphism from sigma to sigma prime, compatible with the boundary parametrization, which I could write as a formula if I had described this here by a formula. Then I need to tell what composition of one morphism is. For one morphism, there's only one composition, and this, let me just write gluing in the same way as we have described gluing of ordinary compositions. So if you want to keep smoothness, you have to do this along collars, but this is an unimportant detail. And then for two morphisms, we have a vertical composition and horizontal. I start with the vertical one. This is induced by, well, two morphisms come from diffeomorphisms. So this is induced by composition of diffeomorphisms. And the horizontal composition of two morphisms finally is again gluing, which of course we have to make precise, but it is essentially one. There's one sensible way to. That's right.
Can I ask?
Yes.
The boundary of the sigma. So you have
So I have, say I start with circles. It's not much more complicated for intervals. So this would be incoming and outgoing. This would be a cobordism of the type that we had so far. But now I can say, well, here I have an incoming circle and maybe an outgoing circle. But here I have two incoming intervals. And then there is some part of the boundary left, and these are free boundaries to which we have some boundary conditions. And drawing certain pictures here would take some time, but in this and the first of the papers, you will find nice pictures. And also, if you look at the talk by Christoph Weigert at the conference 2 weeks ago, you will find corresponding. So
Yes, another question. So could these two morphisms be correlators?
no, they are diffeomorph, but they are represented by diffeomorphism of one morphism, so of the surface.
Yes, the question is if I take all the correlators as two morphisms, is that also give you a two category?
Can you say it again?
If I take the two morphisms to be the correlators, that is a little bit larger than this.
But
This is just some magnetic classes.
you mean mapping classes?
Yes.
But it's essentially mapping classes. Okay.
Yes. But could one take the correlators, the three manifolds?
Three manifold.
As two morphisms.
This is a question of how to extend a modular functor to a three-dimensional topological field theory, and under suitable conditions it is possible. Well, you can certainly do it for the category, but I will not talk about that at all. Now, still, we need more if you want to define modular functor, because it was not just a functor, but a symmetric monoidal functor. So we need also the notion of monoidal and then symmetric monoidal bicategory. And I will be very brief about that. Otherwise, I will certainly not finish today. I'll put this in quotation marks here. So we need a tensor product functor. Which goes from the Cartesian product of B and with itself to B, where functor is in the sense of phi 5. And this is associative and unital up to specified one morphisms. So this is again analogous as what we have for monoidal category. But these one morphisms now, unlike in that case, are not invertible necessarily, but these are invertible up to invertible two morphisms. This is just another instance of the general principle that when you categorify structure become properties become structure. And then, of course, you have a pentagon and a hexagon, pentagon and triangle, but these are not no longer diagrams that commute, but they commute up to two morphisms. Up to invertible two morphisms. So you have a pentagonator, the two morphism, and a triangle. I don't know. It's not instant. And for details about that, you can again look at the paper by Symmetries. Well, it's essentially this PhD thesis, and another not real definition is then a monoidal functor between monoidal bicategories, monoidal pseudo functor. And in short, it's a functor which is compatible with the monoidal structure. So you have one morphism which then for the functor f, which go beyond f of a tensor f of b to f of a tensor b, and analogically for units. And again, these are not isomorphisms, but they are invertible up to invertible two morphisms. I would say this is precisely the definition that we would give knowing this principle of categorification. There's not more to be said. And then definitions which I will not give at all is there's a symmetric monoidal. That's what we need, a functor. And let me just give as reference here, as usual, as for almost all of this, NLAB, and then there is a paper by Day and Split, and a preprint by Schulman. And maybe as a remark here, symmetric monoidal is just like in the category case, the special case of braided monoidal. But now between general braided and commutative, you can have an intermediate set of commutativity. These are called synaptic to monoidal categories. And I don't know anything about them, but there is. So also there is another step, another layer. And now I don't even write this. I'll write it here. This is symmetric monoidal. With tensor product as you really should expect. You can take this union of all these levels. Then for the modular functor, we need also substitute for the right-hand side for vector spaces, and this for me will be the following category, which I call prof. Okay, this is a bicategory. This is a bicategorical version of profunctors, and this is again a symmetric monoidal. First, we need objects. These are small linear categories. Monomorphisms are k-linear profunctors. We call them A and B and so on again. Then a profunctor, let's call it P. From A to B, we will write in this way. And remember, this is the same as a functor from a opposite Kronecker product with B to vector spaces. And then two morphisms are, of course, then natural transformations. Of the functors that underlie the profunctor. Then vertical composition. I start with vertical now. We will see why. Of two morphisms is composition of natural transformations. And this is very easy. And composition of one morphisms is a bit more complicated. Namely, if we have, let's say, a P from A to B and Q from B to C, then they're composite. P composed with Q of, well, it has two arguments. Let me just have symbols for them. this is defined as a coend over the middle category of the first functor evaluated at this argument here and E and B, and then the k-linear tensor product of these with Q of B and 3 variable. And this is a vector space, so here we have just a tensor product of vector space. And once I have this, I can define horizontal composition of two morphisms. This is induced by what I have here. And you have to make this precise, but it's not very hard. And then finally, the tensor product of of this is what I denote again by tensor K, but this is now the Cartesian product of small categories. This means of small k-linear categories. So for the objects, it's the same as Cartesian product, but for the morphisms, I take the tensor product of over K of vector space. And a remark here, I'm using coends, so they have to exist, but they do exist because we deal with small k-linear categories in the domain, and in the codomain we have vector spaces always, which is a co-complete category, and then you can show this. And now, once we have this, we can finally define again what we mean by modular functor, or extended modular functor, if you like. Sometimes people call this also, if I should write this, then it's like open closed. I don't like the word at all. A modular functor, this simply means that I admit not only circles as objects of the covariant category, which people would call closed, but also intervals, and then they talk about open closed. This is a symmetric monoidal functor. I didn't define this, but it's clear what it should be. It's a functor which is compatible with symmetric monoidal structure, and you can make this precise. And I will, if I need for this EL, this reminds of blocks in the sense we use on Tuesday. Symmetric monoidal functor, pseudo functor between these two bicategories that I have described. And I will finish this first half of time. Comments or warning. What I call a modular functor in the following is what I define here. And nothing else, but there are various variants in literature, and you have to be careful. And in particular, this is, if you look at the details version of what some people would call a topological modular functor, where I deal with smooth manifolds here, but the smoothness is just for technical reasons. So everything has a topological flavor. And in contrast to that, you can talk about a complex analytic modular functor. In that case, what is just vector spaces here, together with actions of mapping class loops, which are given by the two morphisms now. would be concrete vector spaces obtained as solutions of differential equations. And in the literature, there is no agreement, as far as I can tell, concerning the question whether or under which conditions these two notions are really equivalent. It is at least claimed that for certain underlying category C in constructions, at least similar to what I will describe, they are equivalent, but there are also critical comments, and I just mention one of them, which is about one particular aspect of one of the arguments connecting those. This you will find in the reference list, and it's just a back page, not anything, any preprint or so on. Okay, so let's have a break. And we have talked about the second part of the title, modular functors. Next part, we will talk about string. What is what you last? Because as I said, I now talk about string nets and the string net construction. And the idea is that you want to have a nice assignment between some surface sigma with boundary in general and embedded graph in sigma, which is colored by some algebraic data, concretely by a category. So vertices are labeled by objects of the category, and more edges are labeled by objects, and vertices are compatibly labeled by morphisms. And to this you want to assign a vector space. In a specific way, namely by using all these data. So you fix a surface sigma and look at all graphs on it, and from that data you obtain a vector space. Well, in the first place, a very large vector space, but then some interesting quotient of freely generated vector space. And the origin of this idea, which was not formulated in this way, is comes from condensed matter physics by Levin Wen in 2005. In that situation, the graph is really given by a subgraph of what physicists call a lattice. So you have, in that case, vertices which carry state space, finite dimensional Hilbert space, and you have a model which is described by, in particular, by a Hamilton operator acting on the tensor product of the spaces. And in order that this is easy to define, you have to take finite. That's fine. But I will not say anything more about that. But instead, I'll really give you a main result, or two main results here. I say them because I'm not sure whether I will have enough time to go into detail about it. So so this is a preview to some extent. There's a theorem, and this is to a large extent due to Kirillov in unpublished preprint, and some additional information is in the paper by Goosen, or maybe it's PhD thesis, I don't remember right now. So what you consider here is a string net, which means such a collection of data colored by a spherical fusion category. See what that is. And I should say already here, for the first part, you need only pivotal, but for the full statement, you need a circle. And the statement is that that these, well, suitably defined, provide a modular functor, which I then write as Sn for stringnet, based on this category C. So this is a modular functor in the bicategorical sense that I described. But at this point, for closed manifolds, one manifolds only. And also the formulation in the original paper is not in terms of pro-factors, but if you can formulate it like that. And then, as shown by Goosen, this extends to a three-dimensional topological field theory, which I have not defined and will not define, but you all have an idea of what that is. And then, canonically, there is an isomorphism between this modular functor and another modular functor known before, obtained from a spherical fusion category, which is called the Tori zero modular functor. So you have a construction, some construction of a three-dimensional topological field theory, which in particular gives you a modular functor. And also, this is not only true for the modular functor, but it again extends to an isomorphism corresponding topological field series. And then non-canonically, you have isomorphisms between the state spaces or vector spaces you have here, sigma, and some additional datum B, which is called the boundary value. If there is a we can still have gluing boundaries of the form, but not free boundaries at this point. That these are isomorphic to morphism spaces of the category Z of C, Schoenfeld center. Remember, this is always braided. And then tensor product over xi tilde, where the boundary value will tell you what these objects in Z of C are. Tensored with, let me call this L of Z of C to the tensor power G, where G is the genus of the surface, and this L is this coend that I defined before, except now it's not for C, but for Z of C. This is not a morphism space. This to 1 of Z of C, or also the other way around. These are fusion categories, so thing is simple. This is again canonically isomorphic. Now this is known already for a long time. Somewhat newer is that all of this naturally generalizes to this relation of your allowed for boundaries, free physical boundaries, and then this is in these papers by with Christoph Weigert and Jan Jan, that I already mentioned. And then I have to say that string nets colored by a spherical fusion category C provide a modular functor. I give it the same name as before of this type, such that there's now no second part here. That reduces to what I had in 518 for the closed part. If I just do not allow for physical boundaries, then I just get what was known before. This is the first statement, and there's a second statement, which says that string nets colored not by a spherical fusion category, but by a pointed strictly pivotal bicategory. And I will have to explain this, but I will do this later. So that I will then denote by B, and correspondingly there will be an index B here. This again gives you a modular functor of this type. And also the two fit together. Remember, from a category, I get a bicategory by the D-looping. And if I take the D-looping of C in this first construction, I will get the modular functor for the D-looping of the second construction. So now what is meant by string nets and string net construction? This gives you what I have to specify are vector spaces. And this goes as follows. Will take a while. And this is for now the ordinary string net construction based on a spherical fusion category. You have the following input data. First of all, a surface sigma with boundary smooth, compact, oriented as usual, and then a finite oriented graph, which I call gamma. And finite means there are finitely many vertices, finitely many edges, and oriented means the edges are oriented. But actually, technically one looks at a given edge with two possible orientations. But I will not go into sufficient detail to make use of that. And then important thing is that I have an embedding of gamma into sigma. And I call this phi. So this is a geometric embedding, but the graph is a combinatorial object, but you can think of it geometrically. And then it is such that image of the graph the part of the image of the graph that is on the boundary of sigma are finitely many isolated points. And in the following when I say graph, I always mean a finite oriented graph embedded in sigma in this way. And then I need, in addition, a C coloring of the graph. And then I say only in words because it's precisely what you should expect, namely to each edge you assign an object, and to each vertex you assign a morphism in R. That maybe I should write to a vertex, assign a morphism, say F, in a morphism space in C. And then, and now I put this in the other order, but that doesn't matter. It's just a technical point. You take the tensor product of the objects that label the edges attached to the vertex, which meet at the vertex, and then look at this morphism space. And now we have to be careful. For a given vertex, x1, x2, x3, and so on, I suppress orientations. If they are oriented in the wrong way, you have to take the dual. And this is consistent because we are in a pivotal setting. But what you have is always a cyclic order. Here you have chosen a linear order. You have to choose a linear order compatible with the cyclic order, and then you have to show that the result does not depend on it. Or actually, you say you do not assign a single space here, but the limit of corresponding of a diagram of corresponding space, which is something you do anyway when you deal to some extent when you deal with slave pattern. And as a consequence of that, we will be able to use this circle graphical calculus that I mentioned. And then we also need to tell what we prescribe as a boundary value for a given circle sigma. Let me just indicate this graphically. If you have a boundary component of sigma, it can now involve also intervals. But let's just look at this simple case. Then we require that you choose finitely many isolated points on the boundary, and technically you may require that on each connected component there is at least one, but maybe you can circumvent that. And to each of these you assign an object of a category. And a boundary value for C is, so this is on D, sigma, this is prescribed on D sigma, but you can also describe it for a graph, gamma. And in that case, you say, this is your graph, then it's a finite collection of one-valued vertices, and to each of those you assign an object of a category. And now you can do this in principle for every graph in the ordinary sense. But remember, when I say graph, I mean embedded graph. So that means that these really have to lie on the boundary of sigma. And also, you need a notion of isomorphism of colorings. You think of two colorings as the same if you replace each of these objects by each of the and this what I forgot here. we have labelings of the edges, and they should be compatible with the labeling you assign to these endpoints. And if you now replace any of those by some isomorphic object and correspondingly modify the morphisms on the vertices, then you regard this as the same data. So this is the first part. And now once we have given all of this information, we can define what a string net space is in certain steps. So first, we say that we take a surface sigma with boundary value as, of this form, where we say that G of C sigma is the set of all C-colored graphs on sigma with boundary value B. And then I denote by Kg of sigma B the vector space, K vector space freely generated by these. So there are very many possible graphs and boundary values for this huge space. And so this in itself is not interesting. But there is once I have this, there is a subspace which I call N of sigma and B. And this is the span of all null graphs. And now I have to define what a null graph is, and I will be quick about that. You have your graph. Some graph, you take a disk embedded into your surface, and you look at the graph that is the part of the graph that is on the disk. You also do this, have to choose it in a non-degenerate way so that no edge here is along the boundary of the disk. And then you assign here boundary values, which are given by the labels of the edges. So here, starting from the graph gamma and this B, you get the graph gamma D on D. Then in this situation, you say that you think of this now as a round coupon in the sense of pivotal categories. So this gives you a morphism. This gives you a morphism in the relevant space x1 tensor xn1, or the other way. Here I have the other way around. Also you find that there is a canonical surjection. Let's call it S, with suitable labels from this big space to the space here. And then a null graph is a linear an element that is in the kernel of this surjection. And I don't want to write formulas because this takes too much time. And then this is a null graph in the first place on gamma V, on the disk V. Now we say a null graph on the surface sigma is a null graph is a linear combination of graphs such that there is a disk, an embedded disk, on which this is a null graph, and outside all the graphs of which you take linear combinations inside the disk are set. If you restrict them to the outside of the disk, so they only differ within the disk, and there it's a null graph, and therefore you call the whole thing a null graph. And then finally you define what you call the string net space, or almost string net space, S n C of sigma and E. This is this large space divided by the space of all null graphs. To be precise, you call this sometimes the bare string net space, even though I will not use this and put a 0 here. So this indicates that there is still something missing. We need some time to specify that. Now, by construction, the dimension of the space, while this is very infinite dimensional, the dimension of this space is finite. And you should not try to see this by taking the quotient, but I will indirectly. Well, actually, the simplest way is to continue a bit and then see at some point that this must be true. Then it should be clear from how I described this here, the graphical calculus for spherical fusion categories is very important. And by construction, you are allowed to use this graphical calculus locally in disks inside sigma. So we can look at smaller disks there and think of those as components and manipulate the rest according to the rules that you have for your category. Then one calls the elements of this finite dimensional vector space string nets, or maybe more precisely bare string nets, but one uses the term also for representative graphs. And one uses also the notation gamma, both for a representative graph and for the class finite that it represents. And then it's clear that when you apply diffeomorphism to your surface, then this will have an effect on the graph. And as a consequence of that, diffeomorphisms act naturally on graphs, and that in fact descends to an action. I should not to an action of the mapping class group of sigma on this vector space. So just like on Tuesday, we deal not just with finite dimensional vector spaces, but they come with an action of the mapping class group. What else did we have on Tuesday? We had compatibility with sewing maps. And here you get also sewing maps because you can sew surfaces, of course, like we did before. And now if you have a graph on both of them, you can try to solve the graphs. You have to be careful. If these are arbitrary graphs, you cannot do it. There's compatibility that the boundary values have to fit. And then it's still not true for graphs, but for classes of graphs, because you can of course move the points around a bit. And then the next step is no, 23 is this. Cannot read my notes. Another definition. Now, take one of the non-manifolds L that we have, and we associate to this, we call the cylinder category. Sil C of L. And again, in index 0, to remind us that we are still in a situation where some detail is missing. So what is this? The objects are boundary values on L. In this obvious sense here, so we have defined this here for one manifold, which we get as a boundary of a two manifold, but of course we can do this in the same way for any one manifold. And the morphisms still C0 between, so boundary values I denote still by B, and between two boundary values I just take the vector space of, but this is the linear category, of course, that I get here from, well, no, that I get from taking, here I need let me first write it. L cross I, L prime, no. L cross I, so I need a I need a two manifold. I take the one manifold times an interval, and on that I need a boundary value. This has two, well, maybe many components, but the two copies, and on one of them I take the B that I have, and on the other hand I take B prime, but then I have to include orientations. I take a dual of one of them, meaning that for these objects that I have here, I take the dual objects, and also I reverse the cyclic order. Like, somehow I look at this from the other side. And then I have to tell what composition is, morphisms, and this is just gluing. And now for the cylinder categories, we can get rid of the zero by observing that in general these categories will not be idempotent complete, and then it turns out to be sensible to look at the idempotent completion. So we define cylinder, again called cylinder category, for a one manifold L, just as the Karoubian envelope of the original one that we had. And remember the objects of the idempotent completion are idempotents in the original category, and morphisms between them are morphisms in the original category, such that when composed from one or the other side with the domain, respectively codomain, it's the same things. It always gives you back the morphism. and the objects are here again called boundary values. But to distinguish them from the boundary values in the unchorobified version, I will use that. And the important ones, now everything is in place and one gets the following result, which is due to Kirchhoff position. In the closed case, Kirchhoff, and then extends to the open closed case. The assignments of sending L to the unchorobified cylinder category for it, and the surface together with a boundary value to the corresponding string net. And to a modular functor, which I call S, again call SN0C. And this is now a statement still at a non-corobified level. Of course, I would not do this if there would not be, but I would not have done corobification here if one would not have an analog for involving those corobified cylinder categories. But for that one needs a little bit more. And before I come to that, well, we need a suitable idempotent completion, but from the definition of these spaces, it's not obvious what that should be. And before explaining that, I want to list very briefly a few properties of the corobified categories. But the main motivation to look at them is they behave much nicer than the uncorobified ones. And let me summarize this at some points in a lemma. First of all, if you take the disjoint union of two manifolds, of two one-manifolds, and then you just get a tensor product, the corresponding vector spaces. The more often I write the L, the more similar it becomes to the C. And then, if I look in particular at the interval, then the original cylinder category, as I defined it, actually is already idempotent complete, so they are canonically equivalent. And also one can show, in fact, it's not hard to see, but for brevity, I will not explain it. It's a good exercise to think about this, that to the interval actually the category you assign is just C. So you have to see that all the possible boundary values are, well, they are in bijection with objects in C, and the corresponding morphism, the possible string nets between them correspond to corresponding morphisms between the objects of C. Now because of this first property, you only need to know the cylinder categories for the interval and for the circle. And for the interval, it's easy. For the circle, it's more involved. So for the circle, you have the following statement. There is a fully faithful, so surjective bijective on morphisms, fully faithful functor from the uncodified cylinder category of the circle to the Drinfeld center of C. You remember Drinfeld center has its objects, morphisms, objects of C and half breakings. And morally, the half breakings you get because you have the cyclic ordering along S1. If you have single out one of the incoming lines here, you can think of this being to the right of the rest or to the left of the rest, and they have to be nicely related, and this gives you a half breaking. Technically, what you do is you show that you deal with a universal coaction of what is called central monad on C. What is a monad? Is an algebra in the category of ender functors of the category, and the central monad often denoted by Z, but I will not use this, sends an object X in C to a coend, namely Y tensor X tensor Y with the dual here. And notice that in particular, it sends the tensor unit to this specific object L that that we have used before. Now this is a coend, so it comes with a natural family, the natural family of morphisms, where I have X here and Y dual and Y here. And using this together with the fact that I have a fusion category, so in particular rigid, I can take this up, and then you see I have Y here. So I get a morphism from X tensor Y to Y tensor X, and you can show this is in fact a half breaking. And using properties of the central monad, and this is Kirillov. Well, he doesn't formulate it in this way. This is theorem 6.4 in this paper. You see that this extends to an equivalence of the full cylinder category of the circle to the Drinfeld center. And then in particular, together with the first statement,
how is that linear category?
They are linear, yeah, and this is
Not as you have
yes.
you didn't define. Okay.
Well, I didn't define the monoidal structure here, but no, this comes from disjoint union. So and then just to trivially together with the first thing here, this gives you a morphism from the cylinder category for the boundary of two manifold sigma in the case that this is the disjoint union of say m copies of the circle to set of C the n-fold the linear product. And this is of course trivial consequence of what I had before, but I wanted to write it down because I will use this notation phi in the last one. So now we still don't have the string nets, and I will not finish this before the break. I wanted to keep this to save time. So let me see how much I can do in 2 minutes. Let's assume that P is an idempotent in the uncarubified cylinder category for d sigma. And then I define something I call P star. This is a linear endomorphism of the corresponding stringnet space. That maps a representative graph here to, maybe I just with our drawing indicate that. So you have a graph on your surface. You have this idempotent here, which is a graph on a cylinder. So you glue these cylinders to the boundary components and get a new graph. And then you have a lemma that P star is an idempotent in the space, in this endomorphism space. And then you can define your carubified stringnet space, your contingent stringnet space, spore, where you have a boundary value B for the uncompactified, for the uncarubified cylinder category, and choice of an idempotent P that you call B, and then you define Sn C of sigma and capital B to be the image of this idempotent P star. So essentially what you do is precisely that you look only at those graphs which at the ends or close to the boundary components look like these idempotents here. And let me just add after time an important statement here, proposition, and this would have been quicker if I had not erased this. The assignments L, now not to the uncarubified, but the full cylinder category of L, and sigma and B to the corresponding stringnet space give us a modular functor, which I call again SNC. And all of this, and a little bit more, to which I come after the break, is just possibly slight reformulation of results by Kirillov and also some part goes in there. Okay, let's have a break. And then I will finish this and come to two further parts. So to complete this part, I'm to erase. Yes. If I take the lemma which I just erased here, then it's easy to conclude the following proposition. let's assume that sigma is connected. Extension of that is easy. And the sigma is of the form m copies of S1. And I have a boundary value consisting of an uncharubified boundary value and an idempotent B in S over there. Then and I take this map phi applied to B, which is an object here. I get an object here, and I write this as the linear product over objects yi, and of course this is ordered. So there is some ordering on which I have to specify, but I suppress this. Then I have an isomorphism of vector spaces between the stringnet space for sigma and B in the category underlying category C. Remember, this is a spherical diffusion category, and the morphism space in the center of C between the unit and then let me denote this by phi tensor of B, by which I simply mean now not the linear product in several copies, but just the tensor product of them in one copy of Z of C in the same, taken in the same order. And then I have here this additional factor taking care of the genus. And in addition, this intertwines the map of sigma action on these two spaces. Remember on the stringnet space, by acting with diffeomorphisms on graphs, we have a geometric action of the mapping class group. On this side, Lubashenko has 95 or so has defined action of the mapping class group, which is completely algebraic and completely non-intuitive. Just on this part, I have some tensor product. This corresponds to insertions. Here I just have the break group acting. There's a subgroup which is a break group, and this is described by gradings, for which I need to be in the center. And here on this object, there is an action of the mapping class group, which Lubashenko defines in terms of a specific presentation of the mapping class group in terms of generators and relations. And this works. That's the fact that you have this isomorphism can be either interpreted as the geometric action here you can understand algebraically, or you say this strange algebraic action here really comes from or corresponds to the geometric action. And now if if the surface is not connected, then instead of such a morphism space, we just have a tensor product for the morphism spaces for the individual connected components. I don't write that down. And I don't want in this context here to talk about possibility to have intervals from instead. I continue to the next part, 5.3, which is now about bi-categorical string nets. Well, I have defined modular functors in terms of bi-categories, but string nets are defined in terms of a category. So it's not so strange maybe to wonder, can, instead of an input substitution category, can I use as an input suitable bi-category and do something similar? And it certainly works for, it should work for one case, namely if I take the de-looping of a substitution category. One aspect of what you have to do is that you need analogs of graphs. These will now be two graphs in the sense that you also have to label two cells, not only 0 cells and 1 cells. And for that, you use the notion of a stratification of your surface sigma. And I don't even write down what that is. Now we have a bi-category B, and you take the objects as labels for 2 strata, the one morphisms for 1 strata, and the 2 morphisms for 0 strata. And well, actually, this is already 5, 3, 4. And in order for this to work, what we have done in the previous cases, we have, while looking at these embedded disks, related the graphs to graphical calculus for a certain fusion category. Now, analogously, we need that B is nice enough to allow for a suitable graphical calculus. And not so surprisingly, this requires in particular that B is what is called a pivotal bi-category. And I will say a little bit about these and even less about graphical calculus, but a few words. Maybe one thing I could say already here, when we go to graphical calculus, we always assume have a strict category. So here we need a strict pivotal bi-category. For that, it's important that there are strictification results for bi-categories analogously to, similar to categories. So what is a pivotal bi-category? It is what you more or less should expect it to be. You first need some analog of a rigid structure, and for that you need the notion of a joint or dual pair of one morphisms, which I will just describe graphically. What is this? Well, it's a pair of one morphism together with a pair of two morphisms, such that I have the following graphs. If I have, let me see how to do A here and B here, then analogically I have A here and B here, and lines, remember, describe one morphisms, and points or small coupons, but I just draw a block here, will be two morphisms, and they should satisfy two relations, which are just analogous to the snake relations for the evaluation, co-evaluation in a monoidal category. So this is one of them, and the other one is where you exchange the variator in this literal line. And then you have the notion of a bicategory of duals, meaning simply that every object in the every one morphism in the bicategory admits such a structure, and then this gives you in particular a pseudo functor from B to B opposite, which is the identity in objects sends a monomorphism to the corresponding dual one morphism, and for the two morphism, it's like two morphism alpha. This would be alpha dual in the well, just what you experience. And then once you have this, then you can define a pivotal structure. On a bicategory with duals, this is just pseudo natural transformation from the identity functor on B to the double dual functor, just like for categories. And for which, now I didn't really define natural transformation. Natural transformation between functors between categories has a component for each object. A natural is which is a morphism, and here I have two morphisms which I associate to in particular two morphisms for each one morphism, and I require that the component at each one morphism. I have components at objects and components at one morphisms, and I require that these are identities. So there only happens something in the first layer of the natural transformation. And this would correspond no, so I said it wrongly. We have maybe I got it. And then what a bicategory is is a bicategory together with the choice of the bottom structure. And a strictly pivotal bicategory is one for which these two functors are actually equal. And I'm not aware of a strict multiplication result that one could use here. So we will use strictly pivotal bicategories. So it will be important that I strictly pivotal from the outset. But I will. And It turns out that for strictly pivotal bicategories, there is a graphical calculus, but it's a bit complicated. Well, you need quite some definitions, and I refer to the papers and to the conference talk by Christoph Weigert for that. But what is important, what we do need are examples. And there are two examples for us which are important of strictly pivotal bicategories, namely the D-looping of a spherical fusion category is strictly pivotal, we can check. Well, actually, here I would, in the first place, have to say strictly pivotal, also for C. But for C, I have a strictification theorem. So I don't have to take this strictly pivotal from the outset. And then the second one, I denote by FR of C, where objects are simple special symmetric Frobenius algebras in the sense I defined on Tuesday. One morphisms are bimodules, and two morphisms are bimodule morphisms. And in this case, how does the dual look like? Of a one morphism is now an A prime bimodule. So we have a situation now in the graphical calculus for monoidal categories, where I have, say, an object M on which I have an action from the right of A prime and from the left of A. And then I can take the dual in the category C. And now I have to define left A prime action. So this is an A prime A bimodule. And I define it in this way. And you can check graphically easily that this indeed gives you a bimodule. And then the pivotal structure is inherited from the strict pivotal structure of C. So that's not much to say. We also, if you remember what I said in the very beginning, I did in the statement, I did not say strictly pivotal bicategory, but pointed strictly pivotal bicategory. I need definition of pointed bicategory. This is a bicategory together with some distinguished objects. And both of these bicategories are naturally pointed, namely here, this is a bicategory with one object, so if I want a distinguished one, I have not much choice. And in this case, this is just a tensor unit of C regarded as a symmetric circle for the example. And now, once you have this, you can proceed analogously as in the case of string nets labeled by a category C. What you need is also boundary values. But this is not much more complicated than what we have before. So we now have distinguished points. They should be labeled by one morphisms. So assume this is a one morphism in the POM category from A to B. And then you say, so this is the label that you have for the point here. And then you say you take A and B as labels for these, for the intervals here. And of course, if you now continue this into your two manifold, this will be a part of your graph. And then the B should be the same label as you have for the two cell, which is adjacent to it and analogously here. And this is, so this is new, new notation, additional notation that you need, but it's not really new information because you already have A and B here implicit by saying like this. And once you have this, you can proceed more or less in the same way as in the previous case. You just say that G of sigma B is now the set of all two graphs, where these are graphs where I also label the, well, which I embed graphs in the surface, then I have two cells and I label them according to the bi category. And compatible, and the labeling has to be compatible. So I don't have. And then once you have this, you look at the vector space really generated by these. Then you again have a notion of null graph, which is completely analogous to what you had before. And then from that you get Sn0b of sigma and B as the quotient of Kg of sigma and B by n of sigma and B as before. And then you can define corresponding cylinder categories for one manifolds, and you can define cylinder categories again as co-rubification. Example that in this case there is not you can easily do that, but if your pointed strictly pivotal bicategory is arbitrary, then it's not clear whether this one is better than this one. Once you have defined these, you can define also co-rubified. I say co-rubified string nets, but it's not really good. Not a very good term, because what you co-rubify is not well, this vector space, but rather the category which you get from these objects E via via these idempotents. There is one, well, there are many details here which I will not say anything about. You can find them in the papers or to quite some extent also in Christoph's talk. But there is one aspect also described in the talk which I want to mention, which because it will play a role also in the last part. And this is the following. There are reasons to want to have compatibility of the prescriptions with embeddings of one manifolds. And in the case with C, now in the case with those one manifolds, there is no issue because there are not so many possibilities of embedding a circle into a circle. There are marked points with which is should fit. But if you have intervals, then you can consider the situation that you have two intervals and you want to embed them both into some larger interval. And then, according to the prescription, you will have marked points here, labeled by one morphisms, and here you will have objects. But for this part here, if you have an object A here, it's clear you will have the same object here. And similarly, if you have B here, you will have an object B here, but a priori you could have some B prime here and some A prime. And then the question is, what do you want to put here? And the resolution of this is that you do not require, do not allow for arbitrary labels here, but that's the point where the pointed property of the category comes in. So this you label by your distinguished object, and then also this you label by this, and then you can forget about it. And similarly, when you this then also works when you embed intervals into circles. And now I have 18 minutes for the last part. This is now coming. Now I come back to conformal field theory. And there is a notion to which we come at the end, which is called universal correlators. And let me see how I. So this is one application of stringnet construction, and the basic prescription that is relevant here. It's rather easy to understand. Namely, we say we look at particular elements of stringnet space, and these we call correlators. And at the end, the statement will be they are actually correlators of a conformal field theory in the sense I defined last time. Namely, the collection of all of them gives you a consistent system for a full conformal field theory. And now S, just like last time, will be a worldsheet in the sense I introduced in 425 with all these additional structure, boundary conditions, boundary fields, and defect conditions, and so on. And I just say this is C-colored stringnet. Represented by a graph gamma, which depends on S and C, which is defined in an obvious way. Namely, remember what our worldsheets were. We had a stratification. Where the two cells were labeled by a phase of the full conformal field series, so by a simple symmetric Venus algebra, and the one strata were labeled by bimodules and the zero strata by bimorphisms. So this is precisely what we have in this bi-category FRC. And But I don't talk about that at the moment as a category. And then I have to, in order for this to make sense, I have also in here on the boundary components I have or they correspond either to field insertions or to boundary conditions, and I have to make contact between field insertions and boundary values in the string net sense. And if I start here from this situation, I have here, well, say I have two this will now be A modules. If A is the Frobenius algebra here, then this corresponds to this object of boundary fields that are denoted by phi and prime. And you can show that this indeed is once you make this precise, is what you get. And similarly, when you have a circle where on this side you have a Frobenius algebra A, here you have a Frobenius algebra A prime. So these are A prime A bimodules, and to this you will associate what I call this object of defect fields. And in particular, then this includes the case of bulk fields. When one proceeds in two steps, first, there is a lemma which says that if S is without physical boundaries, then the space of conformal blocks, as I defined it last time, is isomorphic as a finite dimensional vector space with action of Magniglass group to the string net space for the underlying surface together with a boundary value which is defined from, well, you look at this in the opposite direction. And in particular, this includes the statement that what I define here is really not just an element of some string net space, but in a string net space that is isomorphic to the or can be identified with the correct space of conformal blocks for that worldsheet. Now, this is without physical boundaries. If you include physical boundaries, you could do this directly, but there is a nicer way. We call this complementation. The situation with a physical boundary is as follows. So here you have you have a defect junction between a defect, say A prime defect here, and three boundary intervals which are labeled by M and N prime, which are A modules, and for those there is up to this point no direct place. But then you just realize an A module is the same as a 1, A bimodule, and therefore, so here we would have this would correspond to field insertions, and then we simply say we add to our surface sigma a small part here, which we label by the invisible Frobenius algebra 1, then M prime becomes a defect and M. So this works, and then we have to tell what happens on this new boundary here. But this is again, this is now to be labeled by a 1, 1, a 1, 1 bimodule, so just by an object. And again, we use the fact that there's a preferred object named 1 for C. And then you have a proposition that this way, what you do in 546 together with complementation give a consistent system of correlators. And once you have done all these things, the proof is not so hard anymore. When it comes to mapping, you need mapping class group invariance. But remember, we look not at a full mapping class group of the surface, but at a mapping subgroup which leaves the defects invariant. And that means you have these two patches with a fixed value of A, and you can restrict your attention to those. Now, on such a two patch, if you apply a mapping class, this includes putting a full Frobenius graph here. So this will give you a new graph, but you can easily see that under mapping class, a full Frobenius graph goes to a full Frobenius graph, and the choice of full Frobenius graph does not matter for the result. So you are done. And for solving, again, you can restrict to consider the solving has, of course, to be compatible with boundary values. So you have the whole solving under control if you control the solving of just such a two patch with another two patch labeled by the same Frobenius algebra. And for that, you have to show that putting two full Frobenius algebras, a full Frobenius graphs together gives you again a full Frobenius algebra, full Frobenius graph, and this is very easy. And also, you have to use the fact that you do not put together graphs. They could just not match, but you put together classes. And you put together string nets, which I can represent. Frobenius graph. Sorry? Frobenius graph. Full Frobenius graph I defined on Tuesday. It's a graph with 3 and 1 valent vertices, where each edge is labeled by a Frobenius algebra, and the 3 valent vertices are either multiplication or co-multiplication, and the 1 valent ones are either units or co-units, or if they touch, I should put it here, if they touch, if they touch a defect or a boundary, the label is the corresponding representation models. And 5 minutes left. So this is one main result. But you can do more. And this is related to this fact that map of S is a subgroup of map of sigma S. And if you have many defects, then the subgroup that you get is smaller and smaller, because there's more and more that you have to preserve. And this is not nice, but it turns out that you can do more, and you can show that full conformal field theory cannot distinguish world sheets with different defect networks that are related in a suitable way. So, for example, if you have a defect which is invertible, then this configuration and this configuration with appropriate orientations will actually give you the string correlator, simply because, according to the graphical calculus, the corresponding morphisms are the same. And now, therefore, you define instead, and then you remember that we are talking about string nets, and the defect networks correspond to graphs, but graphs are representatives for string nets. So what we really do is we do not use this graph or this graph, but both graphs represent the same string net, and therefore we have the same correlator. And then we introduce what we call the quantum worldsheet associated to a worldsheet, namely, this is the vector in how do I say this briefly? We interpret the result here as an element in Sn0, not for C, but for not for C or maybe B of C, the looping, but for the Frobenius bicategory for C. Remember, in that case, here really we just have labels A and no Frobenius graphs, but things fit together in such a way that from the worldsheet, or to be precise, from the complemented worldsheet, you uniquely get an element in this space for sigma s on the relevant boundary. No, small b now, because we do not qualify. And then you can show and this is the motivation for calling this a quantum worldsheet, that correlators actually factor through the vector space for the quantum worldsheet, more or less follows from what the way I have described this. So maybe I draw this here. If I start from this big space K G, now for the case that we take the bicategory of Frobenius algebras, from using the prescription for the correlator, we get an element in the string net space for C, using the relation between Frobenius between these two different types of labelings, you can say. And here I have the string net space for Frog. Let me just write sigma. The sigma stands for the sigma I get from the worldsheet plus the boundary value. And then you see that it turns out there's a unique morphism here, where here I take the canonical quotient map. Remember, this is defined as a quotient. And then I call this U core of sigma. And this universal correlator assigns to an element here the correlator for the worldsheet, And that means that because here you do not cannot distinguich, you talk about string nets and not about individual graphs. You will get the same correlator for worksheets which are related, which have different embedded graphs. So different defect networks, but which correspond to the same string net. And for example, that shows that not this possibly rather small subgroup is what is important, but rather you have a different relevant subgroup, which is the stabilizer in the full mapping class group of your quantum worldsheet. So the real invariance of the correlators can be quite a bit larger than what you would expect by just staring at the worldsheet. Concretely, in the situation that I have here, if this is in some analysis, wait. Then in this case, it's clear that your subgroup that you have here will include the Dehn twist around this boundary, whereas here it will not. But in the actual relevant subgroup, the Dehn twist is contained. And one final statement is that another consequence here is that you, by looking at arbitrary defect networks, which give you the same correlator, you describe the correlator in terms of different linear combinations of conformal blocks. And you sweep out the whole space of conformal blocks. So if you forget about defect networks, then for a worldsheet, you get a correlator which is a linear combination of some bases in the space of conformal blocks, and all the other linear, the rest of the space you throw away and it doesn't play a role. And you could say, well, then the Greiber conformal field theory has much more information than the full in this respect. But if you allow for arbitrary defect networks, there will always be, for any linear combination for any element in the space of conformal blocks, there will be a worldsheet, possibly with many defects, such that the relevant mapping class group here, even including this effect, is very small, but there will be some which realize. And this is the end for today, and for now, the end for the course. And I thank all of you here in the room and also those on Zoom for being patient. No time for questions. But as I said, please, I really appreciate it.